Hi everyone. In this video we're going to work on formalizing some notation that we can use for some of the things that we've started doing. So we were doing estimating areas using rectangles, and we just want to build up some specialized notation for that so that as we make that process a little bit more complicated, we can write out what we're thinking without it getting too cumbersome. So for starters, I just want to, this example one is really just exclusively working on the notation. So we want to think about, this is just my first example, the sum of all the integers from 2 to 11. Almost there. You can see that this is doable, but kind of a pain to have to write that all out. So we have a couple of ways that we can start abbreviating. One of them that's something you see commonly is to write down enough terms that you think you've made the pattern really clear, and then you can use ... to omit. So something like 2 plus 3 plus 4, and then we think you get the idea, and then we use ... to leave out the middle terms, and then we write the last term in the sum. So that shortens it a little. We can actually do even better with some notation that at first might look like, why in the world do we want to add complicated notation in? But it is so handy when you have sums with tons of terms. There's no way I want to write this out for sums with 100 terms. So I've included this little graphic just to give you all the things like a reference to look back at. So the sigma, this guy, means sum for us. Whenever you see that capital sigma, that's going to be sum. And then what we're going to use is indexing, which can really confuse people at first, but it's basically just a way of like labeling each term in our sum. So there's going to be the first term, the second term, the third term, the fourth term, and we'll label those by giving them a subscript 1, 2, 3, 4. So the typical element, this is going to be what the typical, I guess I would actually say the typical term looks like. So we're adding all these things together, each thing is a term, and we want to describe the pattern of what's going on with the terms. We then use the index to let us know where we should start and where we should stop. So a lot of times this x sub I is actually more like an x of I. It tells you if you're looking for the ith term, so say the fifth term, then you plug 5 into this formula and it gives you back the appropriate value, the appropriate term. So the bottom number tells us where to start. We're going to start with term number 1, and we're going to stop at term number n, which allows us the freedom to do as many or as few terms as we want. Okay, so I think that's all the vocab stuff there. So now, if I want to use this to write the sum of all the integers from 2 to 11, I'm going to say, okay, sum, and then actually this one is a really simple sum. The terms are just integers, they just increase by 1, but it can really mess with people sometimes as far as like, how do I write that? So really the formula is just, here, like this could work, for example. The formula is that your term, your ith term is just I, so whatever term you're on, that's the value. And then you could say I want to start at, what were we trying to do? I want to start at I equals 2 and I want to stop at I equals 11. So this would be a valid way to do it. You don't have to use I for index, you can use x, you can use n, whatever. So this is saying the typical term is just an integer value, and we want to start at 2 and 11. And a really, really crucial thing with the sum notation is that we should always be starting and stopping at integer values. Integer, yes, I did spell that correctly. And we always increment by 1, so we're not picking up, we don't have I values that are fractions or decimals. It always goes 1, 2, 3, 4, 5, or 2, 3, 4, 5, 6. So if you really just want to add up integers, sum notation is already built that way. Just use your I and start and stop it appropriately. This is not the only way to do this. Let's say I really wanted my index to start at 1 because that makes sense to me, and that was the example I was given above, although certainly not a rule. I could do that, but in order to have my first term be a 2, I would have to say that the typical term is whatever my index is plus 1, and then this would stop at 10. So these formulas both give the same thing. So if we're looking at the first one, it says first plug in 2, and our formula is really simple. It's just whatever your I value is the term. And then you tick up by 1, and you're plugging in 3, and then you tick up by another, and you're plugging in 4, and then you just keep going until you hit 11. This one here says you start at I equals 1, so this was I equals 2, 3, 4, not very exciting. But here, I guess I can write it out this way. If you start at I equals 1, when you plug it into your formula, you actually get 1 plus 1, which is 2. And then you tick up to I equals 2, and you get 2 plus 1, which is 3. And then I equals 3, 3 plus 1, which is 4. And then you keep going until you get to I equals 10. 10 plus 1 is 11. We can see it is giving us the correct thing. The only difference here is the index that's associated with each of these. So now we've associated index 1 with the 2, index 2 with the 3, index 3 with the 4, which doesn't really matter, but just to try to explain to you that those are the same, and that's completely fine. So you might not have exactly the same answer as the key or as another classmate, and that's okay. Okay, so if you're feeling comfortable, this is a great time to pause and see if you can figure out the next couple. We have to get slightly fancier with our formula, but not a whole lot. Okay, so if we want to sum, but we only want to hit even numbers, so we want to sum, and we're going to have to pick out some starting and stopping value for I. The trick to getting even numbers is, okay, so if we just use our I values, they go 1, 2, 3, 4, 5. We want them to go 2, 4, 6, 8, 10. So to do that, it's kind of like adding a slope in there. We need a 2i involved. And then, so this is basically linear. Since we're just increasing by 2 every time, that should be a linear pattern. You can put like a y-intercept in there if you would like to. So you could say, I want my first term to be 4, so initial value 4. And then to make sure that 4 really is your first term, you would start your index at 0, which is fine. You can even start your index at a negative number, but it has to be integer. If we want our last number in our term to be 20, let's see if we want, if we want 2i plus 4 to equal 20, then we need 2i to equal 16, which means our final I value should be 8. And you can always check yourself. Just start plugging in. I'm going to erase my mess here because I know I'm going to stretch out there. So when I equals 0, I get 2 times 0 plus 4, which is 4. And this is for I equals 0. You don't have to write this above, but just so you can see. When I equals 1, I get 2 times 1 plus 4, which is 6. When I equals 2, I get 4 plus 4, which is 8. And this is looking really good. And then again, when you get all the way up to 8, you get 2 times 8, which is 16 plus 4, so we've got 20. Okay, so this looks good. Again, you don't have to put the plus 4. You could also do something like some plain old 2i, and then you just have to start with I equals 2, so that your first term would be 4, and you'd stop with I equals 10, so that your last term would be 20. That would be the same and an equally correct answer. Okay, last one, what if we want the sum of all positive odd numbers? So usually I have someone in a face-to-face class that'll say, well, it's infinity. And that's true, but I just want to write it using sum notation. So this is just practice. So if I want to sum, I want odd numbers. And I already know that if I do a 2i, I get all the even numbers. So really what we need to do here is just shift our starting point. Instead of starting at a 0 or a 4, we want to start at an odd number. And you can do that by adding or subtracting any odd number, basically. So let's say I want to start at 1. I want to shift by 1. So now, if I plug in I equals 1, I get 3. If I plug in I equals 2, I get 5. If I plug in I equals 3, I get 7. So I am getting the odds, and I'm just going to need to be careful about getting the appropriate starting point and the appropriate ending point. So let's see. Actually, I think I built this nicely. So if I start at I equals 0, I get 1, which is the first positive odd number. And then I just want to go forever. So this is an infinite sum, and yes, again, if you add up all the odd numbers, it's going to be infinite. That's okay. I just want to work on representing it. You could also have done, let's say we wanted to do 2i minus 3. You don't necessarily need the parentheses, but they don't hurt to make sure it's really clear that the minus 3 is part of the term. In fact, I would say you actually do need them in this case. I lied. Okay, so here, if we want only positive odd numbers, we can't start at 0, because when I is 0, we get -3. When I is 1, we get -1, still negative. When I is 2, we get 1. So the first I value we can use is 2, and then we still just have to go on forever and ever and ever, so still to infinity. Okay, so hopefully that notation is making a little sense, and just to give you another chance to practice it, I've given you some where I already set it up, and you just have to plug in the values. Plug in the index values and figure out the value of the sum. So again, great chance to pause and actually try this to make sure it makes sense to you. If it doesn't, come back and listen to what I've done. So here we want our index, which is P this time. And again, you can choose whatever letter you want within reason. Lowercase e's are a bad choice, but mostly I don't care. Choose what you want. So P equals -2. So we're going to start with a -2, and then we're going to increment by 1. So then we'll have a -1, and we will have 10 to the 1. Oh wait, did I skip one? I did. 10 to the 0, which is 1. 10 to the 1, which is 10. 10 to the 2, which is 100. And 10 to the 3, which is 1,000. And these even we can rewrite. This is, let's see, this is a 110, and this is a 0.01. So when we add all those up, we get 1,111.11. Okay, so that's the first one. The second one, so we had an exponential pattern going here, increasing by a factor of 10 every time. This one we're going to get a quadratic pattern. So when x equals 0, I get -2 squared, which is 4. So this again is for x equals 0. You don't have to label them, but just so you can see. When x equals 1, I get -1 squared, which is 1. When x equals 0, what am I doing? When x equals 2, sorry people. When x equals 2, I get 0 squared, which is 0. When x equals 3, I get 1 squared. When x equals 4, I get 2 squared. And then last one, when x equals 5, I get 3 squared. So what am I getting? 4, 8, 18, 19. Okay. So that's sigma notation. So if you need to, definitely you can search the internet to see some more examples, but hopefully that's starting to make sense. So summation notation or sigma notation, either of those should bring it up, and you should see it in most textbooks as well. It might be hidden in the Riemann sum section, which is exactly what this one is called as well, Riemann sums. All right, thanks for watching.